So here are two example problems of dilations. Please pause the video and try to do both problems. To do the first problem, notice that we're given that this is going to be a horizontal stretch by a factor of 2. So our formula for horizontal dilations was that g of x is equal to f of x over a. So a is our scale factor, which in this case will be 2. So that means that I'm going to take anywhere I see an f of x and x, I'm going to plug in x over 2. So g of x would be 4 times x over 2 plus 2. I can simplify this because I have a coefficient outside the parentheses and a coefficient inside the parentheses. So this would simplify to 2x plus 2. So if you want to know what this would actually look like, we're looking at a linear function, 4x plus 2, and it has x-intercept here. So this is our original function, f of x. When it has a horizontal stretch, I know that that should end up making it look wider. So 2x plus 2, we will also have the same y-intercept, but its new x-intercept would be 1. So it has a slope that is only half as much, which makes it look wider and broader. In our next example, f of x equals the absolute value of x minus 3. We're doing a vertical shrink by a factor of 1/3. So that means we'll use the formula g of x is equal to 1/3 of f of x. In a vertical shrink, we're just affecting the y values, so you can just multiply by the scale factor. So I would have 1/3 times the entire formula for f of x, which was the absolute value of x minus 3. Then, to simplify, you should distribute. So this would be 1/3 absolute value of x minus 1. And then that is adequately simplified. What this one would look like is our original function. It's the absolute value of x minus 3. So we have 1, 2, 3. And then the new function would be each y value is getting multiplied by 1/3. And so we're going to end up having it look much shorter. And so g of x is shorter, like squished into the x-axis.